Thermal extrusion. What is it? Why does it occur? How can it be avoided? The telltale signs of an elastomer O-ring that has suffered from thermal extrusion is that it no longer has a round profile because the O-ring has taken on the shape of the groove or gland. A frilly edge will be evident on one side or two opposing sides, and there may also be areas of nibbling where sections of the O-ring surface have been damaged. It's a failure mode typically seen in high-temperature sealing applications. The cause is thermal expansion. What is thermal expansion? Elastomers expand when they get hot. The rate of expansion is typically much higher for an elastomer than the surrounding metal hardware. This means at elevated temperatures, the volume of the elastomer will have increased greater than that of the metalwork surrounding it. Therefore, at elevated temperatures, O-rings can expand to fill the groove and then subsequently extrude into the clearance gaps. Thermal extrusion occurs when the elastomer expands so much that it fills the groove and has nowhere else to go other than the clearance gap between the mating surfaces of hardware. The force involved is huge, and as the temperature increases, the elastomer will expand more and more, forcing the hardware apart, which can cause damage to metalwork in the worst cases. A perfect example of thermal expansion is a mercury thermometer. As mercury is exposed to higher temperatures, it expands into the narrow tube along the scale. The rate of expansion is so predictable, it allows us to read the exact temperature based on how much it has expanded. Different types of elastomers expand at different rates. The coefficient of thermal expansion, CTE, is often quoted on material data sheets and will indicate how much an elastomer will expand. If the CTE is not stated on the datasheet and your sealing environment involves high temperatures, it's important to speak with your seal provider to determine the CTE for the elastomer you are using. The CTE value is expressed in terms of the amount of volumetric expansion that occurs with every unit of volume for every degree of temperature increase. The CTE of steel is 15.9 millimeters times 10 to the minus 6 per millimeter per degrees Celsius. Put simply, steel expands 0.00016 millimeters per millimeter per degree change in temperature. As a comparison, perfluoroelastomer expands at 0.00036 millimeters per millimeter per degree change in temperature, 22.5 times greater than steel, as shown on the graph. Let's look at a simple example. The original sample is 15 millimeters wide by 10 millimeters high. The CTE of the sample is 0.05, and the temperature increases 10 degrees Celsius. So 0.05 millimeters, the CTE, times 15 millimeters, the width, times by 10, the increase in temperature, equals a 7.5 millimeter increase to the width. Add the original 15 millimeter width, results in a new width of 22.5 millimeters. The height is worked out in the same way, which results in an increase of 5 millimeters and a new height of 15 millimeters. So, when this sample is subjected to a 10-degree increase in temperature, it will expand from its original dimensions to 22.5 millimeters by 15 millimeters. This graph shows the typical rate of thermal expansion of steel, aluminum, and a perfluoroelastomer. You can clearly see the considerable difference. Let's now compare the rate of expansion for steel and perfluoroelastomer, FFKM, using two samples of the same size at 20 degrees Celsius. As the temperature increases to 50 degrees Celsius, the perfluoroelastomer is starting to expand by 3% compared to the steel, which has barely changed. At 100 degrees Celsius, the perfluoroelastomer has expanded by 8.5%, and the steel has changed very little. When the temperature reaches 150 degrees Celsius, the perfluoroelastomer has expanded in volume by 15%, while the steel is still relatively unchanged. If the temperature continued increasing, the perfluoroelastomer's rate of expansion will continue to be much greater than the steel. At 300 degrees Celsius, the perfluoroelastomer has expanded by 30%, and the steel only 1%. This differential can cause thermal extrusion issues in high-temperature applications. How can thermal extrusion be avoided? Reduce the operating temperature. Use a smaller O-ring so that the thermal expansion is accommodated at a higher operating temperature. The groove size could be maximized to allow sufficient space for the expansion of the elastomer seal at high temperatures, thereby avoiding gland fill. The groove design could be optimized, such as this dovetail groove, so there is space to accommodate the additional seal volume and avoid gland fill. Or choose a different seal profile altogether, such as a lip seal instead of an O-ring, which has less elastomer to expand. If you would like help with your sealing application, speak to the experts at Precision Polymer Engineering, or check out our online Seal Wizard, which guides you through groove calculations, including gland fill, for use with Perlast perfluoroelastomers.